Now in this section, we shall be discussing about the members which are having the axial force also and bending moments also. So we can say that as per the code, we do name them as beam columns. That is, they show the behavior of the beam also and they show the behavior of the column also. So in total, we can say that primarily we are right now talking about the three types of forces. One is the axial force, which we can say that that is like going in a direction of the gravity. Second one is the major axis moment, and third one is the minor axis moment. So we can say that combination of this major as well as minor, that is also known as the what we can name it as the biaxial moment. Biaxial moment. So coming back to the discussion that the name beam column, that is basically subjected to the combined action of the axial forces and bending. So there is a separate section in AS4100, the section number 8, that deals with the codal provision on how to design, we can say, the beam column members. So we can say that the compression members, we know that that is basically because of the force that is coming from the top, and bending moment, that is either because of, we can say, a beam that is like joined from the major axis and a beam that is coming from the minor axis, or it may be because of the eccentricity that is coming, or it may be because of the lateral load, let us say the earthquake, or we can say wind actions. So interaction between the, we can say, axial force, compressive force and bending moment, they produces different kind of effects. One effect is that basically it causes the member to, we can say, buckle. So that is primarily because of what the action of the, we can say, compressive force, and there is obviously an interaction also. Second is that it also reduces, we can say, the bending moment capacity also of the beam column, and obviously the third is that there is a bending also of the major and minor axis. So what I'm trying to convey here is that, let us say we are talking about the axial force. Second one is the bending moment about the major axis. Third one is the bending moment about the minor axis. So all of these, these three actions has to be applied at the same time. And the member itself, that is only a single member. So when we are applying all of these three actions on a single member, it may be a case where the axial force that is quite high, that is as high as, let us say, 90% of the capacity of the member. So in that case, the bending moment capacity becomes very less. So it is not that, if the axial force is high, the bending moment capacity is also high. So what I'm trying to convey here is that, let me just say that in the other parallel words. So there is this, we can say, an interaction diagram that is made in for to study this particular kind of interaction. So this is made something like this. So in this actual, we can say, bending moment diagram, let us say this is basically the N divided by phi NC. That is for the axial force. Let us say this is for the major axis bending moment, that is mx divided by phi mxc. And this is about the minor axis bending moment, that is my divided by phi myc. So we can say that, when the axial force is very high, let us say we are right now talking about here. So in that case, the bending moment capacity becomes very less. But let us say if you're talking about the middle value, that is, let us say phi n star divided by phi n c is something here. So in that case, we can say that the bending moment capacity also becomes higher. So same is the case here also. Or in a case where the bending axial force is very less, in that case the bending moment capacity becomes very high. So we have to study the interaction of these three different kind of actions in the case of the beam column members. So in the ETABS also, as we have discussed, ETABS is calculating all different kind of ratios. It is not that if you are drawing the compression member, it is only checking for the compressive force. It has inbuilt algorithm that is checking for all the different kinds of it is considering all the members as the beam column members. So I hope, let me just draw this in, we can say, a line, a color line. So as I said, axial force is high, bending moment capacity is very less. So same is the case here also. So let us say this is basically the bending moment value. This is basically the bending moment over the major axis value, and this is a higher value of the axial force. So after that, we can discuss about the one more term, that is as I does major axis bending moment and minor axis bending moment. So let us say this is the column member. Yeah. So if we draw the axis, let us say this is one axis, this is the second axis, and this is the axial, we can say, axis. So if we are talking about the axial force, we are talking about the load application in this particular direction. If we are talking about the major axis bending moment, we are talking about this particular direction. That is, let us say this is the I-shaped, we can say, column, and this is basically the major axis because it has the maximum, we can say, sectional modulus, and the steel material is very far away from the neutral axis. If we're talking about the minor axis, so this is the minor axis. In this particular case, we can say this is the minor axis. So minor axis bending moment capacity is very less. Major axis bending moment capacity is higher than the minor axis, and this is basically the axial forces. So this is how we shall talk about the, we can say, different kind of forces distribution. Now coming back to this particular diagram, the code says that the if we are talking about the combined interaction, we can say, formula. So the clause 8.3.4 of, we can say, AS4100 says that N star, that is the actual compressive axial force that is coming, divided by phi ns, that is the capacity. This is the reduction factor, plus mx star, let us say it is a major axis bending moment, divided by phi ms6 capacity, plus my star divided by phi msy. This should be less than or equal to 1.0. Only then we can say this member is safe. So alternatively, it also provides one, we can say, one more equation where we can say that it does not have axial force component, but instead of that it only has the bending moment components. So that equation says that mx star divided by phi mrx to the power gamma plus my star divided by phi mry to the power gamma should be less than or equal to 1.0. Now this gamma here, this gamma is majority of the cases, it is approximately taken as 1.4 also, but it can be correctly calculated by gamma 1.4 plus n star divided by phi ns, and this value should be less than or equal to 2.0. That is a maximum value allowed. So that is the basic interaction, we can say, formula that is given in the code itself. So I hope the concept is now clear to you regarding the combined interaction and all the, we can say, beam column members. So that was the basic introduction, and right now we shall be discussing this with the help of the theoretical example first, and so that you can understand how we can calculate the capacities. So here you can see some pictures also. So if you will zoom in, here you can see that these are basically the beam members, and these are basically, we can say, stiffeners, and in here you can see that these are the cold form sections, that is the Z purlin sections, which are joined with the help of these particular, we can say, plates that are projected outside from the we can say, portal frame members. We shall be discussing and learning this in detail in the separate lecture, but just to give you an idea. So let us say if we're talking about this particular column here, yeah, we can talk about this column, or we can talk about this column also. So on these columns, the beam is coming here and it is also supporting this particular portal frame. So these columns has to take a major, we can say, contribution of the, we can say, major axis moment, high value of the, we can say, axial forces, and a little bit of, we can say, minor axis bending moment also, because majority of the bending moment along the minor axis, that is, we can say, balanced by the girths or by the bracing members. So these are, we can say, tension bracing members which are not yet elongated. Here you can see that there is a sagginess in these tension bracings. So usually, after installation, they are tightened at both the ends with some pre-calculated tensile force also. So coming back to the, we can say, calculation. So let us assume that the section type that we are right now talking about is 416 to 67.1 UB, and the steel gauge is 350 Newton per mm square. But if considering the thickness is, we can say, maximum is 12.7, that's greater than 11 mm. So we have to deal with the reduced Fy value of 340 Newton per mm square and tensile strength of 480 Newton per mm square. E value, we very well know that is 20 to the power 5 Newton per mm square. And elastic, we can say, sectional modulus, that is this particular value, and plastic sectional modulus, obviously that is higher, and that is this value. And second moment of area, also known as moment of inertia in some countries, that is basically this particular value, 2958 into 10 to the power 5 mm to the power 4. And radius of gyration about x-axis, that is very high, that is a major axis, so this is high, 185.7. And radius of gyration about y-axis, that is a minor axis, this is less, that is 41.17 mm. So after that, let us assume that this particular section has to deal with, we can say, major axis bending moment of 125 kN meter, minor axis bending moment of 30 kN meter, shear force of 200, and minor axis shear of 75, and the axial force is approximately 200 kilonewton. So this is basically the, we can say, capacity maximum utilization, and this is the combined interaction that we had studied in the formula. That is contribution of axial plus contribution of major plus contribution of minor, that all value should be less than or equal to 1.0. So first of all, we shall start with the, we can say, length of this particular beam column member, that has been considered as 8 meter, and minor axis it is considered as laterally supported, that is 0 mm. So section slenderness, first of all, we do need to calculate. So if we're talking about the section, that is, section is compact. First of all, for the major axis flexure, so BF minus TW divided by 2TF, the value comes up to be 8.3, less than 16. D minus 2TF divided by TW, that value comes out to 58, that is less than 115. So lambda, we can say, the value here, that is basically less than 16, so the section is compact. After the section slenderness for the minor axis, for minor axis also it is compact, considering that this particular value lambda EF is 8.3, and section slenderness is basically 8.33, that is less than 9. So after that, first of all, we shall be talking about the axial compression forces, that is the section 6 of AS4100-2020. Axial force in our case was 200 kN. Net area of the cross section is 8581 mm square, that is this particular value. Yeah, the 8581 mm square. So if you're talking about the nominal section capacity, so here we can do the same calculation as we have done above. So we can say that the effective width of the web, that is basically 328, and AE value, that is 7726. Now before I start discussing about these calculations, you do need to understand that we are talking about the net area and we are talking about the effective area. So if we are talking about the net area or gross area, they have been considered as same, that is AN equal to AG. So that is this particular value, that is in the denominator. But effective area is the different area which can be calculated as per clause 6.2.4, that we shall be discussing. Why we are doing that? Because we have to find out the form factor KF, that is clause 6.2.2. So KF is the factor that is required when we are trying to calculate the compressive capacity of a particular structural steel member. So if we open the clause 6.2.2, So here you can see that form factor is basically A divided by the AG, that is effective area and gross area of the cross section. And if we are talking about the clause 6.2.4, it gives us formulae that help us in calculation of, we can say, effective width of the flat plate element. So that is basically B multiplied by lambda EY divided by lambda E. Now this is the same equation that we are using here, that is lambda EY divided by lambda E. So if we're talking about the effective width of the flange, that is basically 90.8 mm. And if we are talking about the actual width of the flange, that is basically approximately, we can say, 190 divided by, we can say, the half here. That is approximately 95 mm. So if we do the math here, that is 190 minus 8.5 divided by 2. So this value comes out to be 90.75. So if we go into the value that has been written here, so that is the same value. That is, there is no as such reduction in the effective width of the flange. After that, if we're talking about the web slenderness, so web slenderness is approximately 58, but however, the width is 40, effective, limit is 45. So if we do the same type of math here, that is, we can say, effective width of the web. So we can go into, we can say, calculation here. So 454 minus 12.7 minus 12.7. So this value comes out to be approximately 428.6. And if we go into the value that has been calculated here, so that is quite less, that is 328 here. So what has been done here is that what they have done is 45 has been divided by 58. So we can multiply this with 45 and divide it by 58. So this value comes out to approximately 332 mm. That is the same value that has been approximately considered here. So we can say that the effective width of the web has been decreased. So effective area shall also be decreased. That is 7726 instead of what we can say 8520. Let me just show the number again. Against 8581. So effective area is basically 7726. So that is what we can say 7726. That shall be divided by 8581. So the form factor comes out to be 0.9. So that has been considered here. So nominal section capacity is nothing but Kf, that is the form factor, into An, that is the nominal area, and multiplied with the Fy, that is in our case 340 Newton per mm square. So this value comes out to be 2626, which when multiplied with 0.9 gives us 2364.1. Now the actual force that is actual coming on the beam column member is approximately 200. So 200, which when divided by 2364.1 gives us 0.085. So that is the same value that has been written here. So we do have a very high, we can say, axial capacity margin. After that, if we want to discuss about the nominal member capacity in the major x-axis, so major, and by default it is named as x. Now if we want to discuss about the member capacity in the major axis, so that is basically, we can say, effective length has been considered as 8000 mm. And if we're talking about the modified compression member slenderness, so that is basically lambda L by R multiplied with square root of Kf, that is form factor, multiplied with Fy divided by 250, that is 340 divided by 250. So this value comes out to be 47.671. So if we would have been, using only lambda L by R, so that is not correct if we're talking about the bending interaction. So compression member factor alpha Ax, that has been calculated with the help of this particular equation. Now this compression member factor, member section constant, this slenderness ratio, compression member imperfection factor, compression member factor again, member slenderness reduction factor, and nominal member capacity in compression. So all of these calculations can be, we can say, skipped if we simply find out this particular, we can say, lambda nx, and we can simply multiply with alpha cx from the AS4100 itself. So we know that lambda nx is 47.671. So we can simply, refer to table 6.3.3c. So for, I shape section, it is 0, alpha b is 0. And right now we are talking about the lambda value is approximately 47.671. Approximately we can say 48 itself. So we are dealing with a number in between these two values, that is 0.884 and 0.861. So it should be, on an average, can be, taken. So this number is coming out to be approximately, we can say 0.871. So we can say skip all of these calculations and simply refer to that from the table itself. So after that, we can multiply 0.871 with the ns, and the value comes out to be 2289. After that, we can say design of member capacity in compression, that we can simply multiply 0.2 with this number, and this value comes out to be 0.097. So this is basically the member capacity, we can say, considering the major axis. Nominal section capacity that has been calculated with the help of the effective cross sectional area. Similar exercise we shall be repeating about, we can say, design for major axis xx bending moment also. So this all of these values here, if we want to start calculation, first calculation is NOMB. So pi square EI divided by KL square, the value comes out to be 9123. Moment application factor, that can be taken from clause 4.4.2.2. We can refer the clause also. So this is the clause here. Here you can see that the delta B is the moment application factor for a braced member, and that can be calculated with the help of this particular equation. So to calculate the CM, we have to follow this particular formula, 0.6 minus 0.4 beta m, and that should be less than or equal to 1.0. So considering all of these equations, we can find out that delta B value is approximately 1.022. That is a maximum of either 1 or the calculated by putting CM divided by 1 minus n star divided by NOMB. So on the basis of that, we can amplify the bending moment. So our original moment was 125 kN. By multiplying with moment amplification factor delta B, the moment that needs to be considered as 127.8. Similarly, if we're talking about the section moment capacity for bending about the principal axis, so we can find out the effective sectional modulus, nominal section moment capacity. We very well know this particular formula, and nominal section capacity with axial force. Now this is the new formula, that is MRX, that needs to be either minimum of this or MSX. So we can simply jump on to clause 8.3.2. So this is the formula that needs to be referred. So for compression members where Kf is less than 1, in our case Kf is 0.9. This is the formula that needs to be considered, and basically the title is the uniaxial bending about the major principal axis. So to calculate, we can say MRX, which means the nominal section moment capacity reduced by axial force. We need to use this particular formula, and if we jump onto this particular formula, we can put all of these values that we have calculated above. On the basis of that, we can find out this particular value, that is 502.9, and that needs to be multiplied with 0.9 to find out the bending moment capacity, that is 452.6. So the ratio mx star divided by mrcx, this value comes out to be 0.282. After that, if you're talking about the segments with full lateral restraint, end moment ratio, that can be taken as -1, and maximum segment length, clause 5.3.2.4. So you can open the refer this particular formula, and on the basis of that, it has been calculated 1059, and segment length has been taken as 0 mm, considering that it is having full lateral restraint. After that, if you're talking about the member capacity from section 8.4, so this value comes out to be approximately 408.6, considering that we need to multiply MSX with this particular formula, that is 1 minus n star divided by phi n cx, as per clause 8.4.2.2. So design member moment capacity exceeds the design bending moment. Similarly, we can refer to minor axis bending moment also, that is from section 5.1, where the CM value is 1. And OMB, we very well know that can be taken calculated with the help of this particular formula. that is 2.9 into 10 to the power 6. And after that, moment amplification factor that can be taken from this particular formula. So design bending moment in our case shall be same, that is 30 kN per 30 kN meter. Similarly, we can find out the section moment capacity for bending about the, we can say, principal axis. So this value basically comes out to be, we can say, the capacity comes out to be 70.3 equations. So clause 8.3.3, that also we have already discussed. So uniaxial bending over the minor principal axis. So for that, basically we can say that doubly symmetrical eye section which are compact, we do need to refer to this particular formula for the minor axis. That is 1.1 n msy multiplied with 1 minus n star divided by 5 ns to the power 2, and that should be less than or equal to msy. So the same formula has been taken here, 78.1. So similarly, we can find out the, we can say, member capacity as per section 8.4 also. So this ratio comes out to be 0.466. Similarly, we can find out the shear capacities also. So shear capacity is very simple. That is d into tw is the cross section area of the web, which needs to be multiplied by Fi, that is 340, again multiplied with 0.6. So the value comes out to be 787.2, which needs to be multiplied with 0.9 to gives us the final answer of 708.5. So, similarly, we can find out the gross cross-section area, fan, flange, design, shear capacity. So these are the same, set of formulas that I'm not repeating here again. This is the important thing, that is member subjected to combined action. So, we, if we talk about the interaction, we studied the gamma factor. So gamma factor is minimum of either this or this. So this value comes out to be 1.485, which needs to be inputted here. So, and here also. So considering that interaction formula, value comes out to be 0.436, that is less than or equal to 1. Similarly, if you're talking about the interaction formula as per clause 8.4.5.1, so this value comes out to be 0.54. So I hope the calculation is clear to you, that the basic concept that we have to study the interaction. And how we study the interaction, we first of all check the bending. We check the axial compression force, and we check the capacity, axial capacity. Then we check the bending moment that is coming about the major axis. Then we check the bending moment capacity about the major axis. Then we check the minor axis bending moment, and then we check the minor axis bending moment capacity. And then at the end, we do need to check the interaction also to find out that the ratios and summation to the power gamma, that should be less than or equal to 1.